bear in mind. Okay, so you mentioned denoising, and again, we don't necessarily, we just throw away kind of the higher components. But the other thing is compression, right? And that is what I'm going to quickly show you. It's not a financial example. So we're gonna load, and if you guys kind of follow, it's scikit-learn. There is scikit image. There is scikit image. We import IO and we read a JPEG file, right? And we see that it's actually ND array is a numpy array. So we see that the type of this thing is actually a numpy array, an n-dimensional array, which is the underlying type of numpy arrays. And the image has come back as a numpy array, and it's an image, right? We can use matplotlib, right, which is the same thing we use for plotting, pylab, matplotlib. We can use it to display the image, and this is Lena, right? This is one of the classic examples that we have in. It's one of the classic examples that we have in image processing. Right, this is a classic image. Like you find it in lots of textbooks on image processing. So we got Lena with some noise, right? The matrix is 300 by 300 because the image is 300 by 300. Now, if it were a color image, you would get a three-dimensional tensor, effectively, right? So a higher dimensional matrix is called a tensor, right? But I mean, it's an ND array. I mean, an ND array you would have 300 by 300 by 3. You would have the red component, the green component, and the blue component. I sort of deliberately converted this image to grayscale, so you just get a flat image. But then you would have to work with different layers individually, or what I did. I mean, you can, or somehow merge them. But anyway, but this is a grayscale thing. So okay, so n. Let us think of rows as our observations. So we have n equals to the number of rows, which is going to be 300, and the number of features, let us think the columns as features, and it's going to be 300 as well. It doesn't have to be that way, right? I just chose to think of rows as observations and columns as features, right? It's an arbitrary choice. I could have chosen something else, and so I could have chosen, I could have transposed this thing. But in this case, let us think of rows as observations and columns as features. And let us do PCA in it. Let us do the full set of 300 principal components, right? And then we do PCA fit to the image. And let us plot a very, very useful plot to is the magnitude of these eigenvalues, right? So we plot the lambdas, which is the PCA dot explained variance underscore. We just plot them, and you see how quickly it tails off. Right, the variance tails off very, very quickly. I mean, I fairly arbitrarily kind of drew the line here, but I mean, like I could have drawn it somewhere else. Right, I then picked 50 principal components. Right, and then basically I could have just thrown them away from this matrix, but I mean, I now call PCA again, saying keep the same. It's going to be the same numbers, but only keep the first 50. I mean, I could have moved this line a bit further. You can see, I mean, like I really could have put it there, right? When this variance tails off. But remember, I don't necessarily know whether there is some useful stuff here, or whether it's all noise. Okay, and you see now the shape of this transform. Then I apply the transform, and which matrix does? Okay, which matrix? In my notation from the lecture notes, which matrix does PCA.transform image return? Which matrix? Which capital letter did I use for that matrix? No, W is the eigenvectors, right? When I do the transform, I get the Z, right? It's Z equals X times W. Yeah? X centered times W. Yeah? So the scikit-learn returns what we call the components. Is actually I call the eigenvectors weights. They call them components. I call them weights. I call Z, the transformed data, the components. So, all right. So PCA dot inverse underscore transform returns this Z matrix. But note that the image transformed image is 300 by 300. Image transformed is 300 by 50. As a very basic image compression technique, and we'll see, we'll compare, I could have just stored this image underscore transformed, right? I mean, I would save a lot of space now. Yep. So I've thrown information away, right? But you see, that's another application. It's compression, right? It's not lossless. It's a lossy compression. I've lost some information, which I cannot automatically recover. But I have reduced the memory. You know, I could work with this reduced structure. So I could do it for either saving space or saving time, efficiency. Right? I could save time by doing this as well, because I could do processing on this stuff, right? I could do linear algebra on this stuff, right? And it's smaller than the original thing. Yeah. So that's another application of PCA effectively that we found. It's lossy compression with some information lost. But let us see. So I mean I could plot this thing, right? I don't know what this thing actually means, right? In fact, it would be interesting to plot it. I mean, I'm not sure what it even looks like. I mean, it might be interesting to plot this thing. I don't think I've actually done this. So let me see what this thing actually looks like. So, you know, if we plot the original image, hopefully this is going to get evaluated and we'll see. So here we have the original image. Okay, so I'm going to do this stuff. I'm going to fit this to the image. Okay. Fit it again for 50 components. PCA transform. Okay, well, let us insert cell above and let me plot image transformed. Well, that's what it looks like. Right, this is what the transformed image looks like. And I'm not sure whether we can actually zoom in. Right, this is the result of this transformation. Now you can kind of see that, you know, that there is, you know, for these things there is more going on, and then it sort of calms down. Right, that's the result of this transformation. So you can visualize this on an image, right, what the principal components are. But now let us see, let us transform it back, the inverse transform. But of course we've only used 50 principal components. It's not going to be the original image, right? So this is computing this it's WZ or W transpose, whichever way it is. We're applying W. Remember the the matrix of these, it's an orthonormal matrix. So it's the eigenvectors are orthogonal to each other and have unit length, and the inverse of such a matrix is the transpose of this matrix. Right? So the inverse transformation is just the transpose of our W matrix. Yeah? So the original image, this is the original image, and this is the image with dimensionality reduced. After transforming back this thing where we threw away the most of the higher principal components. So you see, as you mentioned, this transformed image, reduced image is less noisy. If we kept all components, all 300, we would have gotten the original image back. But you see that as you pointed out, we have reduced noise. Can you guys see this? Right now, noise is reduced. But again, there is still some noisiness going on there. It's not like beautifully noise-free. It's an interesting result, right? But we've also lost some information. If you look at her lips, she's quite a good-looking lady. But anyway, but the point is, if you look at her lips, you see that actually it's pixelated now. a little bit more than it was, right? So we have lost some information, yeah. And you know, and if we kind of picked, say, if we kind of picked what would you look like, if we instead of 50 principal components, we just took, say, 5. Well, this is all we've got now. That's the transformed. This is the transformed image. That's the visualization of our Z matrix. Okay, so it's very noisy. It's very noisy. Let's get rid of the noise. Okay, now she's definitely not good looking. Right? We know this is what happens if you get rid of all the. She's quite scary now, actually.
The noise is gone.
But you can sort of just about see. You know, it's quite interesting. It's quite interesting what this looks like. You see these. You get these patches in the image. I wonder what's going on. Do you see that you now have these like... Do you see that it's now quite patchy? Do you see that there is like some natural... Do you see there is like some grid? Wow, I didn't expect to see that. Guys, those of you who do signal... do you see that there is now like, you know, there are like these like rectangular regions here now? I don't know why that is happening.